So, yeah, I was asked to give this talk about some of the work we've been doing on electron microscopy of metal halide perovskites. And I wanted to sort of divide it into a few different parts where we talk a bit about how do we get images from electron microscopes in the first place, and then how do we apply it on metal halide perovskites. I'm not going to go into a whole lot of detail about solar cells as such. I assume most of you are kind of familiar with the concept of solar cells and probably also with perovskites to a certain extent. So I'm really going to try to focus more on how do we apply these really powerful electron microscope techniques to study these very interesting materials. So my overview, here's a bit of an overview. So the first thing I'm going to do is introduce electron microscopy in general, just so we all know kind of what we're talking about. I'll talk a bit about what an electron microscope is. I want to talk a bit about why we use electrons in general, rather than photons, and I'll talk a bit about how we then see these electrons. How do we detect them? And then I'll talk a bit about one of the biggest issues we have with working with electrons in general is this beam damage, and particularly related to how we study hybrid perovskites. So in this case, it would be MAPI, so methammonium lead iodide. And I'll talk a bit about how do we actually use electrons to get atomic resolution images of a different, very, very similar perovskite from ruthenium lead iodide. And if we have some time, which I don't think we'll quite get to, but we'll see, I'll talk a bit about how we can study what happens when we mix these organic cations together using a very, very low dose technique, so selected area diffraction, which maybe we'll get to, we'll see. So starting out, first of all, what is an electron microscope? Well, in the simplest case, it's something that fires electrons at something else and then records what comes out of it. And probably you want to use the nature of electrons to look at something that's much smaller than what other things typically could look at. So an electron microscope generally is sort of reasonably good approximation for most of the microscopes you'll encounter. You get electrons that are extracted from a very fine tip, either by heating up the tip or applying a voltage, typically both. You then accelerate these electrons onto something using a bias, typically sort of 500 volts to 300,000 volts. There's some microscopes that have gone up to 1 million volts, which is not quite necessary with modern techniques, but it makes some pretty interesting microscopes. These accelerated microscopes then move down an evacuated tube. And in this evacuated tube, you then have electromagnetic lenses sitting around the electrons, and these lenses are then able to focus the electrons into a very fine beam, and the beam hits whatever you want to look at, and then the electrons interact with the specimen, whatever it is you want to look at, and that will generate a signal of some kind. If we collect the signal, we can get a lot of information about what it is that we want to look at. So this is one type of microscope that many people will be familiar with. It's a scanning electron microscope. It's not going to be the main focus of the talk, but I do want to talk about it a bit because it's quite commonly used by people. And in this case, you can see it's a tabletop microscope where you scan a beam across a surface in a raster pattern, and you collect information as the beam goes on. And typically use it to look at just the morphology of something. And one of the cool things about this is you can look at bulk samples. Basically, anything you can fit in the vacuum chamber, you can look at. And you can get pretty good resolution, much better resolution than your visible light microscopes, but not quite atomic resolution at this stage. And so here's a TEM. As you can see, if you compare the size of the computers, the SEM is quite small, the TEM is quite big. So this is a 200 kilovolt transmission electron microscope. In this case, we have at the top an electron gun that then fires electrons down towards a sample that kind of sits in the middle. This sample has to be very, very thin, so less than 100 nanometers ideally. So we put the samples on little grids that are specifically meant to go inside this microscope. You can sort of spread the beam, you can focus the beam, you can do all kinds of cool stuff. And with these ones, we can achieve atomic resolution. So this is a 300 kilovolt microscope. You can see they get quite big. They often need to be built like into a special room that has special damping effects on the floor. Here you can see Judy loading a sample, filling a microscope up with liquid nitrogen. And the little bulb you can see towards the middle here, that's where you stick the sample in. So I always thought it's quite funny that the electron microscopes are such big instruments because this is what we're looking at. So maybe 3 millimeters across is a TEM grid. And this is where we need to put everything that we look at. So you can see we're not actually probing a whole lot of material, which is obviously one of the issues with TEM in particular. is that we're only seeing very, very small amounts of material at a time. So we need to generalize quite a bit. So why do we want to use electrons in the first place? Well, optical systems have sort of limitations on their resolution due to the wave nature of radiation. So when photons come out, they behave as waves. And the wavelength of the waves that you use to look at things with determines the resolution that you have in an optical system. So I'm going to do some really basic optics. I apologize if everybody knows this, but I think it's good to already know, like we all know what we're talking about. So you can think of an object, a tiny, tiny object that's a little aperture. And when you shine light on something and the light comes back out again, the light is emitted as kind of like a spherical wave if you have a small enough object, and we end up with this diffraction. And so if you look at it from the top, no matter how small your object is, it will have a wave coming out with a certain spread. And this spread is determined by the wavelength of the light that you're probing with. And now you can imagine if you have one spot, like one single object sitting somewhere in space, that's fine. But if you have two objects sitting next to each other, well, if these waves are quite big, then they will overlap. And so resolution, when we talk about resolution, is how closely can two objects be to each other before we start having problems distinguishing them. And if we look at what the resolution of an optical system with using sort of visible light, we can use this Abbe equation where we basically have our resolution is given by some constant times the wavelength, the radiation times this, which we call the numerical aperture. And so if we plug in some numbers that we use, say green light, we use 500 nanometers and a numerical aperture of 1.6, that's a pretty good visible light microscope, we get a resolution of around just under 200 nanometers. Now that's not very good for perovskites, especially if you have grains in the order of less than 100 nanometers. You might not be able to distinguish two grains sitting next to each other. So to the rescue, electrons. I Googled Electron Man to see if anyone had done anything, and this amazing drawing came up. Thank you, Alexander Steck on Reddit. Electrons are really cool in the way that, as the boy told us, and through our quantum mechanics that I'm not going to go into, but electrons are both particles and waves. They have this particle-wave duality. And the wavelength of electrons is given by this equation over here. So basically, Planck's constant divided by the momentum. And so what you can see here is we have a mass that's given, and we have velocity. Now, this velocity here is really important because if we accelerate electrons, we can accelerate them to a really, really, really high velocity, so close to 80% of the speed of light in using a couple 100,000 volts. And so in a typical microscope, this is sort of at 100 kV, we'd probably be running at 200 kilovolts more commonly, but we get a wavelength of 1,000, couple of thousands of a nanometer, a couple of picometers, and we get a resolution that's less than 1 nanometer. So now we can actually start distinguishing things that are on an atomic level, or at least what this means is that we can focus a beam to allow us to do this. So we can see tiny, tiny things with electrons, which is very, very cool. But then obviously you might be thinking, well, really, can we? Because when you look at something with your eyes, you don't see things that are a few hundred nanometers apart, you see them as an object, right? So I showed you that it's possible to focus an electron beam to a tiny spot, but our eyes, they can't see electrons. And in fact, it's probably not really good for us if we try to look at electrons accelerated to 100 kilovolts. Probably not very good for our eyes in the first place. So we need to understand how we actually see things using electrons. And so this is where this interaction that I was talking about before comes in. It's quite, well, when we have electrons, because they have a mass and they have a charge, they interact quite strongly with anything that we're shooting them at. So if you can imagine here, we have an electron beam and it hits. In this case, we have a thin specimen. So this could be something sitting on a TEM grid. We have different interactions happening at different depths. So if you look at SEM, most of your electrons that you're looking at will be these we call secondary electrons. They're electrons that kind of get knocked out by the incoming electrons. They come back out again, and they give us morphological information. We also can sort of ionize or raise electrons to higher energy levels that then fall back down again. And when they fall back down again, they will emit an X-ray. This is what we then call characteristic X-rays. So each element has a characteristic spectrum of X-rays emitted. Now this comes slightly deeper into the volume, so we get lower resolution for EDX in a bulk sample in this case. We can also have some of the electrons passing straight through, So this would be sort of what we call transmitted electrons, and this gives us morphological information, so how thick is the sample, and we can have some electrons coming through, but then scattering outwards as they pass through the sample. So this could be something where we get diffraction, for example, or I'll show in a second a bit of what we call LADAF or HADAF, where we get sort of actual analytical contrast based on how much scattering we're getting. But as you can see, we can get like a lot of different bits of information just from firing electrons at stuff, which is really cool. And so it's very tempting to just fire a whole bunch of electrons at a material and see what comes out. But that's a bit of an issue, which we'll see in a second why that gives some problems. But just to illustrate why we get contrast in SEM. So basically the number of electrons that are emitted when you hit with electrons is determined by the morphology. So you can see down here at area A, we have 4 little lines coming out. It's a flat surface. But if we get closer to an edge here, then you can see that some of the electrons that would have been otherwise emitted, they actually go back into the material. So we get fewer electrons coming out here. So this area will be darker. We measure the electrons that come out. So this area will be darker. Area B will be darker than area A. And then finally, when we get close to sort of an edge here, we have more electrons able to make it out. So we get a brighter contrast. And if we record all the electrons that come out in a raster way, we can get these beautiful SEM images. And this is just to show, we have kind of an average contrast in the middle, and then towards some edges, we get quite a lot of strong contrast. So we have more electrons escaping, and we have fewer electrons able to escape down in the holes here. But what I'm going to focus a bit more on is TEM, because that's really sort of the trickier of the techniques. Like my supervisor used to tell me for my PhD that you can learn SEM in a week, but it takes a PhD or more to learn TEM, and I'm still learning. So yeah, it's very true. There's a lot of stuff you can sort of play with. But we have, in this case, you can imagine this kind of looking inside a TEM. It's kind of squished together, so it's not very representative. But we have electrons coming down from the middle. We have some apertures that block some of the electrons out, so we can control how many electrons we get in. We have this what we call the probe-forming lens. It's basically just a big set of magnet coils kind of sitting around that focus the beam. We have some scanning coils down here, and then we have the thin specimen. And so, like I was saying, we get X-rays coming back out, so we can stick an EDX detector, or electron dispersive X-ray spectroscopy detector in here. We can record some of the X-rays coming in. And then as the electrons move through the sample, we have some that are scattered outwards at quite high angles, is what we call HADAF. And so the heavier atoms in a column scatter more, so we can get a really nice contrast relative to atomic number. And we can also have electrons passing straight through, so we can put kind of what we call a pixelated detector. It's basically a camera that takes electron intensity down here. So we can get a whole bunch of information through in a TEM. And so this is a really good example of some of the cool things that we can do. So this is a HADAF, so high angle annular dark field image of strontium titanate, so different type of very stable perovskite material. You can see some of the spots are brighter than others. And this is because these ones are heavier. The brighter columns are heavier, so they scatter more than the lighter columns. And then the darker ones are oxygen. Oxygen doesn't scatter very much. But what we can do is, while we're measuring this image, we can also actually record the X-rays that come out. And so we get basically atomic resolution X-ray information. This is scanned over and over again, like many, many times, and requires loads and lots of electrons. So we can't really do it in our hybrid perovskites. But we can get these atomic resolution maps of these materials, which is, I think, personally super cool. So I'm going to go into a bit about beam damage and how we image our hybrid perovskite materials. So we need to talk about sample preparation first. Like I mentioned, the samples have to be very, very thin. And so typically people use what we call focused ion beam milling, where you use heavy gallium ions to kind of mill out or dig out a little slice of material. Typically around 100 nanometers, you can do down to 50 nanometers. It's very, very cool if you want to look at devices, but it's kind of like analogous to digging a hole by firing, a machine gun into the ground. You can dig the hole, but you have a lot of, bullets going in, you have a lot of gallium being deposited, and you might actually damage the structure that you're looking at. So we tried to grow some single crystals to try to figure out how we can, how good this technique is. And we grow a single crystal, we mill a little slice out of it, and here you can see this is the diffraction pattern that we obtained from this area. Now, you don't need to understand diffraction patterns very well, other than just kind of understand that the more well-defined, the more regular they are, the more sort of crystalline, the higher crystal quality they have. And here you can see this little ring going around. Some of the spots are a bit smeared, which kind of for us indicated that this is not a pristine sample. There's some beam damage involved. But you still see, you know, the diffraction pattern is not completely messy. So there might still be some crystallinity left, some quality crystal in the material. So we did this 5 years ago or so, and this year, some work that I was doing with Alvin Zhou and Songhua Kai from Hong Kong, they actually showed that you could do focused ion beam milling of a device or a lamella of a single crystal and then still get atomic resolution. So here they show some very nice defects along these lines here. But you also see there's quite a bit of damage going on. So you get some darker blobs. So what we can see here is we still see the atomic structure, but we have quite a lot of damage going on. And also this year, our good friends in Cambridge published a really nice little paper about where they did focused ion beam milling of a device and compared the luminescence spectra. And so you have the PL spectrum sitting here around 1.6. And then they measured the cathodoluminescence, which is basically photoluminescence, but instead of exciting with photons, you're exciting with electrons, and you get a spectrum. So they see that the first scan shifts the spectrum sort of 0.1 EV to higher energies, and the second scan shifts is another 0.1. So then the question is, you know, it's not completely ruined. You still kind of get a cathodoluminescence signal. Is it 100% representative of what you see in a solar cell? Perhaps not, but you might be able to get some information from this preparation technique. So as long as we're kind of aware of what the limitations of our techniques are, you know, there might be some things we can learn from focused ion beam milling. But we decided to kind of go with this thing where we deposit our films directly onto a TEM grid. And we get a really nice film. This is an example of a 300 nanometer Mathy thin film, which we imaged over time with a very low dose, so 2 electrons per square angstrom per second. So this is incredibly low dose. And you can see after 2 minutes, we already start seeing crackings forming. And as time goes on, we see more and more cracks. And after 7 minutes only, we see quite a lot of cracks going on. Now, a regular TEM session lasts anywhere from 2 to 8 hours. So if you expose your material for that long, you're definitely not looking at the pristine material. So you need to keep moving to new areas, basically, which is a bit of a pain in the butt. We can see this happening on a crystallographic level as well. So again, here's a diffraction pattern. So you see some spots kind of coming across diagonally. You can ignore those, they're from a separate grain. But you see, other than that, we have a really nice, beautiful sort of square diffraction pattern. We see these double spots down here in the bottom left-hand corner. This is indicative of crystallographic twinning. But you can see after just 1 minute of exposure to electrons per square angstrom, those double spots are gone. So now we've lost these domains, and we start seeing the appearance of additional spots, which tells us that there's some ordering going on as we're exposing it more and more. But eventually, that ordering disappears again. And if we focus the beam in the same area, we see a completely different diffraction pattern. Now, this looks quite pristine. You know, if you were to give me this and say this is a crystalline material, I'll say, yeah, for sure, definitely crystalline. But it's definitely not the material we were looking at before. We can see how this changes from a chemical perspective as well. Here we're measuring the ratio of iodine to lead. And so in our pristine perovskite, we have 3 iodine for each lead. And in our precursor material, we have 2 iodine for each lead. And here you can see with all of the different dose rates. So this 2.1 here is what we did before. The 200 is getting closer to sort of normal imaging. And we have very, very rapid deterioration of the material under all the conditions. We can plot our ratio as a function of total number of electrons, and we can see we get quite a good correlation. So it's almost like the dose rate is irrelevant, it's a total number of electrons. So we need to look down up here to get pristine material, which is sort of a dose budget of less than 100 electrons per square angstrom, which is incredibly low. We can also see how the actual emission spectrum degrades over time, just for good measure. Here's the CL emission, so again, like photoluminescence, but with the electrons instead. And our signal decreases really, really quickly. This is not because we're forming additional lead iodide. We expect to see a peak around 500, but simply what's going on is the electron beam is just frying the perovskite here in this case. So it's quite a high dose, quite a high current and quite a low voltage, but we still see quite a lot of damage. So what we need to do is turn down the dose rate. So basically turn the light down all the way, and we use contrast enhancing apertures. So we're losing some resolution, but we're getting better contrast in our images. And what we can see is something like this. Now, this is one of my favorite pictures I've ever taken, I think. So this is a methylammonium lead iodide thin film on a TEM grid. And we can see these beautiful stripes coming across. And so many people who work with Mathias thin films have found these to be sort of ferroelastic domains of different types. We were able to then, with our electron microscope, we can basically go in and probe within a grain, well, what's happening. So if we're looking at these grains here, let's see the initial film, we can go in and stick an aperture within a single grain, and we get a diffraction pattern. And here's where we see these double spots that indicates that it's crystallographic twinning, which I'm not going to go into detail with, but this is crystallographic twinning. And after only 4 minutes, we see the stripes are gone, double spots are gone, even though we still have a really nice diffraction pattern. So we have to be really, really careful. This is like incredibly low dose imaging. So at least we know kind of what we're looking for. So this is some example of what we can do with lower magnification diffraction studies. I'm going to talk a bit about atomic resolution imaging, because that's the sort of holy grail. I think a lot of people, every time people talk about electron microscopes, are like, oh, can we see atoms? And yes, you can. It's actually really cool. You can. So we published this in Science a couple of years ago, a year and a half ago, and this is really the first time that we were able to see the sort of intrinsic crystallographic properties of these thin films in real space, in real life, where we can see grain boundaries, we can see defects, we can see all kinds of really, really interesting stuff. So this is actually really exciting that we were able to get these results. So if any of you are interested in trying this for yourself, for our studies, we did thermally evaporated FAPI thin films directly evaporate onto TM grids, around 30 nanometers. We did between 30 and 90 nanometers thin films, so they're quite thin. We got preferential orientation around the 100 axis, and we imaged using very low dose conditions at 200 kV, 200 kilovolt acceleration voltage. And we used low angle annular dark field imaging. So we're kind of probing the electrons that get scattered slightly outwards, not all the way outwards, but kind of slightly outwards. We filtered the whole thing with a Butterworth filtering, which is just a sort of a signal to noise ratio improving filter. It's a linear filter, so there's no funny things going on. So first thing we need to sort of make sure of is beam damage. And you can see here, when we're using 66 electrons per square angstrom, so less than the 100 we were talking about before, we get a really, really nice crystallographically correct image of our perovskite here on the left-hand side, on the right-hand side as well. But you can see as we start scanning, so this is 3 scans, we see quite a bit of change. We have our back areas forming, we're losing material. We scan another, what is this, like the 9 times in total? Well, we have actually a completely damaged material. Now, this is very stable phase. This doesn't change a whole lot. So if you're scanning at 2000 electrons per square angstrom, you're not going to see a whole lot of change, which is really confusing because you're going to think that your material is super stable. And crystallographically, you could misconstrue this to being perovskite for some, if you're just looking at crystallography. So that makes it quite tricky. So our damage takeaways for this is we need very, very few electrons. So we can maintain a crystal structure up to around 66 electrons per square angstrom. We can see grain boundaries up to around 200, and complete damage has happened before 600 electrons per square angstrom. So just to compare, if you want to take a regular atomic resolution image, so the one I showed you before requires thousands or tens of thousands of electrons per square angstrom. And typically, if you want to do your EDX mapping, so the X-ray, the really cool X-ray mapping requires hundreds of thousands to millions of electrons per square angstrom. So these are some things we need to keep in mind when we try to figure out what we can actually do. But when we do take really great care, we can actually see some really, really cool things. So here's quite a low magnification. It's not quite SEM resolution, but it's definitely getting there. Quite low magnification image of a FAPI thin film. And if we zoom in here, we can see some really cool things. So we can see, for example, low angle grain boundary. We can see a higher angle grain boundary. We can see a triple junction between 3 grains. We can see extended planar defects. We can see secondary material inclusions of some kind. And over here, we parked beam for a very brief moment. As you can see, it's just kind of burned a hole in it. So what we can see, for example, we have some sort of qualitative understanding of our grain boundaries. For example, we have very little distortion caused by some of the triple boundaries. So they're very crystalline all the way up into the interface. But we also have some grain boundaries that might have amorphous material associated with them. Or maybe this is a sink for point defects. So we get more point defects here. It's quite common that grain boundaries are defect sinks. So they might attract defects over here. We also have what we call align point defects. So it's almost like there's a gap sitting in the little triangle here, a little hole, which was a weird crystallographic phenomenon. It's not quite sure how that happens, but we're looking into that. We can also see that we have very little long-range distortion introduced by these planar grain boundaries. So it's not like you have a grain boundary and then the effects ripple outwards. Like these perovskite materials are quite unique in some ways, that they just kind of absorb all of these weird defects going on. So once you're 1 or 2 unit cells away from an interface, then we actually don't see an influence of the grain boundary. Again, we have more different types of aligned point defects. Look like there's no a little hole, and we see no distortions around it, which is really, really weird. Basically a perfect square. We can also see stacking faults, where we have sort of a shift of a half a unit cell. You're kind of coming up one crystal direction, you shift half a unit cell, and then you keep going upwards the other way. So this is locally the inclusion of a tiny amount of lead iodide. We're now working on what type of lead iodide this is, but this could be why, like, because it's quite a flexible structure, we can introduce a tiny little bit of lead iodide locally, and it doesn't change a whole lot. We also see these really cool edge dislocations, which is formed by crystal planes being wedged in between other crystal planes. But also this seems to be absorbed within 1 or 2 unit cells, so that's also quite strange. We can see lead iodide inclusions. And you see what I've highlighted here in yellow is lead iodide sitting within a perovskite lattice. And what's really cool is if we draw a line across, you see in the top line here, we start the blue lines in a white spot and it keeps going down and it ends in a dark spot. So there's a shift between the crystal in the top and the crystal in the middle of a half a unit cell. Now that means that these 2 domains are crystallographically sort of separate. They're not connected. So they have to have grown out of different sides of the lead iodide. So the lead iodide is kind of like a delineator between 2 domains. And that means that the lead iodide can act as a seed. And so that's probably why this lead iodide, the formation of perovskite from lead iodide is so easy, that we can basically have the crystallographic scaffold there. We just stick some perovskite onto it and it works really well. We also can see how the strain is across this interface. If we draw a line here across, this is the same image as before. We measure the strain across and we have very low strain, so less than 2%, which indicates that these inclusions of the lead iodide is very, very benign within the perovskite. I should sort of mention, this is not the lead iodide you would see if you were to look at an SEM image. You get big white flakes. This is something that grows within the perovskite crystal that might be invisible to SEM. And so we're just about to submit a paper about the actual phase that we're looking at here, what type of lead iodide this is and which properties it has when it's interfacing with the perovskite. Here's an example of some really cool strain mapping, again, going across a low angle grain boundary. So the strain is in different directions. So strain in the X direction, in the Y direction, and then shear strain. And because of the way the strain maps work, you can only map 1 grain at a time. So we have to have a map for the grain on the left-hand side on the top and a grain for the right-hand side on the bottom. And we can see something really interesting going on at the interface. So if you follow the interface, you have high strain, low strain, high strain, low strain along the interface in the X direction. But if you're looking at the shear strain, that actually changes across the interface. So this could have some implications for very, very local crystallographic and electronic properties of these low angle grain boundaries. And then I think I'm running a bit out of time, so I'm not going to go into detail with our selected area diffraction studies of these mixed cation. But if you want to hear a bit more of that, please do ask. We published this last year in June. So yeah, I'm just going to skip a bit ahead. Basically, we're mixing stuff where we see differences in crystallography, and we can correlate that to, we can say why that happens, little domains of some delta phase going in the cubic perovskite. And basically, the solar cells with the fewest defects have the best solar cell performance. I guess that's like a 30-second takeaway of that paper. So just to conclude, electron microscope and microscopy in general is a very, very powerful way to characterize these perovskites. We need to make sure that our dose is lowered by several orders of magnitude relative to typically what you would do for other high-resolution imaging settings. Atomic resolution STEM can tell us a lot about this sort of local crystallographic environment, so grain boundaries, defects, material inclusions, all kinds of other things. And we use diffraction studies. We can talk about the overall crystallography of the film with grain-to-grain resolution. And we can correlate this with device performance, which is very, very cool. So I just want to thank all of my collaborators, both from Monash, where I did my PhD, which is the second paper I talked about, and then obviously from the University of Oxford. And I want to thank you. And so please go ahead, ask me. I'm expecting at least 3 questions, and I would love a lot more than that. So thank you.